Alright, so we're going to look at another situation now involving Newton's second law for rotation. So remember that the net torque is equal to the moment of inertia times the angular acceleration. Okay, so we have this situation where we have a block attached to this disc, and so essentially it's like wrapped around it, and it's going to pull down on it and cause it to rotate. Now, all the times we've talked about pulleys, we've said they were massless pulleys because of the amount of the kind of stuff that we're going to have to look at right now. Okay, because we have to take into account basically the fact that this is going to rotate. Okay, which means that if this was a massless pulley, this mass would just be in free fall, but it's not because it does have mass, and so gravity is both causing this mass to accelerate downward and causing this to rotate at an accelerating rate. Okay, and so we actually are going to need, though, three sets of equations here. We need to use our net torque equation. We also need to use a Newton's second law equation, since we have linear motion right here. And the common variable that we have between these two equations is acceleration. Okay, and the key here is that this block is not slipping on the pulley, and so that is what allows us to do that. And the way that we can connect those is by saying that acceleration is equal to alpha times r. Okay, and this is going to allow us to connect these two equations together. So if we look at the hanging block, we have gravity pulling down on it, and we have the tension of the cable pulling up on it. Okay, if we look at the disc, we have one torque caused by tension, okay, causing it to rotate. And so we can start with any of these equations. I'm going to start with the net torque one. Before we do, we have to talk about sign convention. So we say that counterclockwise is negative, or positive, I'm sorry, so that means that this direction will be positive, okay, which means that we have a negative torque caused by the block pulling down. Okay, so let's go ahead and do this. So the sum of the torques is going to be equal to I alpha. The only torque acting here is a negative one caused by that hanging block, and it's acting at a radius r. Okay, the tension is what's pulling down on it, right, like we showed here, and it's acting at the distance r from the center. Okay, the radius of the block. All right, so that's our first equation. Now let's go to our Newton's second law equation. So the sum of the forces will be equal to m times a. Okay, and we have the upward force T and the downward force mg. Okay, we have T here and here, so we can take tension and put it into this equation. So T is equal to ma plus mg, and so we have I alpha equals negative parentheses ma plus mg times r. Okay, this is a cylinder. If we look back at our table, we say that for a cylinder, 1/2 mr squared is our moment of inertia. Alright, so we'll call the mass of this disc capital M, so we'll say 1/2 capital M times r squared times alpha equals negative ma plus mg times r. Okay, and so now is when we need to make the a and the alpha the same. Okay, it says we're solving for angular acceleration. I'm actually going to do this. I'm going to take this right here. I'm going to say that I think this would be easier to solve it. So divide by r, and alpha is equal to a over r. So I'm going to put that in here. So 1/2 m r squared times a over r equals negative ma plus mg times r. So what we can do now, this r will cancel with that one. We can divide this one over as well. I'm just going to get rid of that. And so in this case, actually, the radius won't even matter, even though we did know what it was. We'll use it later to calculate the angular acceleration. Okay, so 1/2 times m times a equals negative of ma plus mg. So we distribute that negative and add this over, so that 1/2 ma plus little ma equals negative mg. Okay, almost there. We'll go ahead and substitute in values, and we can factor out the a here. So 1/2 m plus m times a equals negative mg. Okay, so let's substitute in values and solve for a. Sorry about that. As I tend to do, I kind of used up all my space, but substituting the values, dividing over, you get the acceleration of this falling block is about negative 4.8 meters per second squared. And so that's not actually what we're looking for. We're looking for angular acceleration, but it's a quick solve from there. We're also looking for tension, so let's do that first. So we go back to this equation, t equals ma plus mg. So t equals ma plus mg. T is equal to, we'll factor out the m, so 1.2 kilograms times negative 4.8 meters per second squared plus 9.8 meters per second squared, and we'll get 6 newtons there. Okay, and then to find the angular acceleration, we'll go back to here. A equals alpha r, or alpha equals a over r. We know that a is negative 4.8. R is equal to 0.2 meters. Okay, and so that's going to give us, let's see, I think negative 24 radians per second squared. Let me double check that. So yes, so we get negative 24 radians per second squared for our angular acceleration. Alright, I know that was a lot. You might benefit from kind of just scanning back over that problem. Okay, but this is kind of the heaviest application we'll have for Newton's second law of rotation. Now, before we finish, I just want to point out one thing. The most common mistake that I see with a problem like this comes right here when you write in your torques. Okay, remember that torque is the force times the radius. Okay, a lot of times I see students leave out this radius here, and it throws off all the other work in this whole problem. Okay, so don't forget that torque is force times radius. Okay?